You've probably seen the quadratic formula in school. It's the magic key that unlocks the solutions of any quadratic polynomial. Equations of the form ax squared plus bx plus c equals 0. What's more interesting is that there are also formulas for solving cubic polynomials, and even quartics, equations of degree 4. They're much messier, but they do exist. But surprisingly, there's no formula for the general quintic polynomial. Wait, what? Every quintic polynomial has exactly 5 roots. So why can't we just write them down using a neat formula? Here's the catch. There is no formula built from a finite sequence of the usual arithmetic operations, addition, subtraction, multiplication, division, and taking nth roots, that works for all quintic polynomials. But how could anyone possibly prove such a thing? You can't just try every formula and fail. There are infinitely many possibilities. This was the exact problem that puzzled mathematicians for more than 350 years, until a 20-year-old Frenchman, Évariste Galois, cracked it in 1830. So let's rewind and remind ourselves what solving means. Take the quadratic again. If we, quote, complete the square and manipulate the equation only using the allowed operations, add, subtract, multiply, divide, and taking roots, we eventually arrive at the quadratic formula. Cubic and quartic polynomials can be solved in the same way, though the derivations are much harder. But notice the pattern. Every time we're basically shuffling terms around and applying the allowed operations, like following rules of a puzzle. In fact, solving equations feels a lot like solving a combinatorial puzzle. That's where Évariste Galois comes in. He realized that the key lies not in grinding through formulas, but in studying symmetries. His idea was, if f was the field of numbers in which our formula will be written, then to express the roots with our operations, we require some symmetries in the roots of the polynomial with the base field. Galois showed that if the group of symmetries, also known as the Galois group, is a cyclic tower, meaning it follows a simple rotational pattern, then it is possible to express the roots using radicals. But if the symmetries aren't cyclic, if they're more complex, then no combination of these operations can express all the roots. In other words, the equation isn't solvable by radicals. This insight reframed the problem completely, from solving equations to understanding the deep structure behind them. Suppose you start with a base field, like the rationals, Q, and build the smallest field that contains all the polynomial's roots, let's say K. Then you ask, what are the symmetries of this larger field that leave the base field untouched? These symmetries form a group. Today we call it the Galois group. This was the first time anyone had used the idea of symmetries of permutations to settle a problem in algebra. That insight not only solved the quintic mystery, but also laid the foundations of modern group theory, which today appears everywhere in mathematics, physics, and even cryptography. Let's see some examples. Quadratic over rationals. The Galois group has just 2 symmetries, swapping the 2 roots. That matches the idea of square roots, so a formula exists, the quadratic formula. Cubic over rationals. The group turns out to be the symmetries of a triangle. This group has subgroups corresponding to square roots and cube roots, which is why cubic formulas can be written using these operations. Quartic over rationals. Similar reasoning shows a solvable group, hence there's a quartic formula too. Quintic over rationals. The Galois group here is S5, the full set of permutations of 5 objects. Inside it sits A5, which is simple. It has no smaller building blocks. That structural rigidity means no formula in radicals can capture the quintic's roots. So the general quintic is unsolvable by radical formula, not because the roots don't exist, but because the group structure is too intricate. In fact, the solutions of the general quintic can be expressed using elliptic modular functions, which encode the symmetries of A5. Quintic over reals. The Galois group has just 2 symmetries, which means we can write all roots of polynomial using radicals over R. But that doesn't guarantee that there is a closed-form formula for it. So existence of simple symmetries doesn't mean the formula exists. It just says the formula is possible. And that's why the story of the quintic is so remarkable. not just because it couldn't be solved by radicals, but because it led to a whole new language of symmetry, revealing that the structure of equations is often more important than the solutions themselves.